Welcome. Today we're going to be talking about surface integrals. And recall, we've done this before, where we have a set D, which we put in a two-dimensional space U and V. So, sorry, these are just scalars, not vectors. And then we have a point, every point in there. There'll be a U and a V right there. And then we map with a vector function to XYZ space. Like that. So, and we embed, which allows us to embed this two-dimensional object. We always think of R as creating or sort of warping this this flat area of like that. So it creates some surface. So what we do typically is we want to, if we take some patch of area, which we'll call delta U there, delta V, and that gets mapped again to this, what I'll call delta S. And that little patch is what we call delta A, right? And so we learn that a surface area was equal to what we'll call the double integral over the S surface ds. So we're adding up all the little patches. That's all that means. But we can parameterize or operationalize our integral by knowing how this little area here gets warped and bent and transferred to this area here if it gets stretched. And so we can recast the integral in terms of an integral over our UV space rather than our X, Y, and Z space. And what we do though is we have a dA now representing the infinitesimal little area patch, but we have to put a little volume distortion. And the volume distortion is equal to the partial of our vector function in terms of U times the partial of our vector function in terms of V. Okay, so again, RU is just going to be the partial of our vector function in terms of U, and RV is our partial derivative of the vector function in terms of V. And what we have to do then is take the derivative of each component in terms of U and V respectively to create those vectors. And then we take the cross product of those, which gives us a little patch of area there, and we times it by dA. Okay, so we know that. So now what we're going to think of is this space here, this XYZ space. There's every point in XYZ. We're going to define some other quantity called f of x comma y comma z. Right? F, and that could represent some concentration, some quantity of interest that lives in a fourth dimension. But for every point in the entire three-dimensional space, this function is defined, at least in some region that we're interested in. But what we're really interested in is finding this integral, so a general surface integral, is just going to be the integral over a surface of a function that is embedded in 3 dimensions. All right, so what we're talking about then is, so not only when we add up these little patches of area, we also evaluate the function on those little patches. So that little point then has an f of, if that point there is xi, yi, zi, then that will be fi, y, I should call this j, and that's I'll call k, fi, y, yj, and zk, that it lives on this little surface here. So all we have to do then to define this integral is do the same thing we've done before, but now we're just going to write the double integral over d, just like before here, and then we're going to evaluate f at the point r of u comma v, which is the value of the xyz coordinates that are restricted only to the surface. So we don't care about points out here. The function values of points that are away from the surface are of no concern to us. We just want to integrate this three-dimensional function on a two-dimensional surface embedded in 3 dimensions. And so again, we take our RU cross RV, take the norm of that, dA. All right, so that's what we call our general surface integral. And it's just the basic idea of a surface area integral, but what we're doing is we're now evaluating a function on that patch of surface, and then we add them all up over the domain of integration defined by D, our set. Okay, so that's nice. So that, a use for this or an application, it'd be, if you have some three-dimensional space, but maybe you have a surface embedded in that space that, has some sensors on it. And maybe you have some quantity that lives in the whole space there, right? It's all over 3 dimensions. But when it's in contact with this surface, we want to know how much of that substance, or the concentration of this substance, is only on the surface. So you can think of this as being important for maybe filtration, or I don't even know. But the idea is that we only care about the value of the function on the surface, so that's all we want to add up. Okay, so that's good. But the real application, so this is sort of the mundane version of surface integrals. The real interest we have now is what we call a surface integral for flux, or we'll just call it a flux integral. A flux over, or I should actually say through, a surface. All right, so this is a surface integral, and what we need then, we're going to get a vector field, which in this case we'll just say is P, Q, and R, just like before. And it defines, perhaps, it could be a velocity field. That's the most concrete. We could also have it be an electrical field or a gravitational field, and so on and so forth. But the idea is that a velocity field of a fluid, let's say. So we want to know if we have a velocity field in three-dimensional space. So there's some fluid flowing around in three-dimensional space like this. What we want to be able to do is, if we have some sort of surface that's sitting there, we want to know what happens when how much fluid flows through our surface. Now you can see this is incredibly important if we're talking about or thinking about how maybe filtration can happen, or anyway, what we want, again, the goal here is we want to compute total flux of fluid, or it could be an electrical field, which we call just the electrical flux, but we'll think of it as a fluid today. A total flux of a fluid through a surface. Okay, so let's operationalize this thing a little bit. So again, we have our set D, and that's in our UV space. And we map that with our vector function, UV, and we map that to this surface living in three-dimensional space. Okay. All right, and then through that surface, we have a little patch that lives in UV space, and that gets mapped to some point gets mapped to some surface there, and we call that our two vectors there. And then what we have now is a vector field now pushing through this surface. So sorry, I'm going to rewrite that. The vector field, I want to do it a little bit like that. So that's our vector field. So at other points on the surface, of course, there'll be other vectors defined. So remember, F is defined through the whole entire three-dimensional space. It just keeps going. But we only care about, just looking at this patch, we only care about just the point, just a representative point going through just that one spot right there. And we want to know, if this is a fairly good approximation, we want to know what the flux is through that little patch of surface, which we'll call delta S. All right, so in general, so not in general, if the special case, if F is normal to S at the patch delta S, that is, if we have our little patch there, and if F is at a 90-degree angle of that, then the flux will be, through that little patch, will simply be, well, let's think about the units of this, right? So the units are, for a fluid, so if F is a velocity field, then that means we can think of it as meters over seconds. To just give a concrete example, right? So those are the units, right? And then a flux, then, that has to be yeah, so a flux then has to be volume over seconds. So we're talking meters cubed per second. So what we're saying here, that's meters cubed. Okay, so volume over seconds, and we have velocity fields of medium over seconds. So to get the flux, then, we need to times F, at least the magnitude of F, times delta S. And that's in the case when this is normal. So the whole thing is just going right through that surface. So of course the units of this will be, and so delta S, of course, is meters squared, right? That's the units, if we just want to put it in standard scientific notation. So of course that will create meters cubed over second, which is the desired quantity. So let's however, in general, F won't, in general, be normal to surface, right? So the idea here is we have our little patch of surface, but F might not be going perpendicular to the surface itself. So what do we have to do here is, if this is our little patch of surface, we can actually define the normal for that surface. And we want to find out, so the goal then here is to find the component of F that is normal to the surface. So recall then that F, this is our F, it can always be decomposed into a component that's normal and some other component there that is coplanar. It's within the plane of our patch of our surface, right? So we can always write F in terms of, so the normal vector, of course, is always a unit vector. It has a unit length, just a length of 1, plus some other vector, which I'll call P, means it's planar, within the plane of the surface. Now, if that component of the vector, of course, isn't actually crossing, the surface. It's so we don't have to worry about it, but we'll put it down there. We'll just say that that's equal to B times P. So the part we're interested in, because we want flux, and what we want then is just that number there. We want the amount that's actually passing through the surface, not the amount that's passing that's traversing the surface, because that's not going through the surface. So the flux then is going to be this value A. So how do we get it? So we know that F, so the dot product is what's going to help us. Remember, it is the amount. The dot product then is going to be F dot N. Again, and that's going to equal our A value, which is going to be our flux. All right, so remember now we have a surface, and everywhere on that surface is defined. It can be written as, it's the set of R of U and V, such that U and V are in this set D, right? That's how we define it. So that then defines N of U and V, right? And we also can define F, the vector field on the surface, as F, the vector field evaluated at R, U, and V. Right, so these are two vector functions. So this is an R3, and this is an R3. But when we dot them together, so F dot N, this will be a one-dimensional function, right? So in general, what we have here is F, sorry, wrong lowercase here. Now we have a function in just 1D, right? So we go back to our original definition of a surface integral. And what we had was, if we had some function, f, and we just evaluated it at r of u comma v, where that was a function that was living in 3 dimensions, ds, what we're going to say then is that is our f. All right? So then this integral becomes, the flux then is the integral over our surface, and an f becomes now this function of the vector field dotted with the normal of the surface times a little patch. So that equals our total flux. All right. So the question then is, how do we find n? So we want to find n. So goal now, so again, our total flux is going to be equal to the double integral over our surface of our vector field dotted with the normal to our surface, ds. Okay, capital S. All right, so we need to find, so what is this normal? How do we find it? So the goal now is find an expression for n, okay? So recall we have our set U, our set in U and V space. We have our vector function of U and V, embedding the surface in 3-dimensional space. And every little patch gets deformed into this little thing right here. We have that vector RU, and we have the other vector there, RV. Right, so if I do a cross product of those two vectors, I produce that a vector that's in the direction of our normal. So it turns out our normal vector will be RU cross RV. But to make it a unit length vector, we have to divide by RU cross RV. And that just makes it a unit length. Okay. Recall also then that ds was equal to the norm of RU cross RV dA, where dA was in this plane. So then our total flux, which we said was this, we can write as the integral over our domain D in the UV space of our vector field evaluated at the vector function, dotted with, now we're going to replace the normal vector with this quantity here and multiply ds by this, and we see that those are going to cancel. So what we're left with is just RU cross RV dA. So there is our constructive formula for finding the total flux through a surface S. Okay, so that's nice. So let's try doing an example to close out this problem. So I'm going to just make myself one more sheet of paper so I have enough to get going here. So I'm going to talk about, we'll talk about our example. We'll just do one example here. And we're going to have the vector field f of x, comma y, comma z is equal to z, y, x. All right, so this is a funny vector field. Let's see what it looks like. It's pretty wild. It's difficult to draw in 3 dimensions. So here's our x, y, and z coordinates. So when we're at the point 1, 0, 0, the x value then creates, that's 1. The other ones are 0, so we just get a vector pointing straight up. But if we go to the z-axis, we go out unit, we get a vector pointing that way. If we go out the y-axis, we get a vector going that way and that way. And if we go out on the other side of the x-axis, it goes that way. So this is really wild. It's really difficult to see what's going on here. There's a lot of swirling vectors going on. We don't know if this is rotational, if this is irrotational, what exactly this looks like. But let's try to compute a flux. We're going to compute the flux. Through a sphere. Sphere of radius 1, centered at the origin. Okay, so we can define the sphere as rho squared is equal to x squared plus y squared plus z squared is equal to 1. Okay, all right. So so the question then is how to find the normal. The normal vector, let's find that normal vector. So again, we have so what are the ingredients we need? The definition then, the flux is going to be the integral over our sphere of f dot n ds. Okay, and so we need to find this normal vector. And okay, if we draw a sphere, we know it's always going to be pointing directly out away from the origin, right? Everywhere we go, the origin's in there. We're just going to be pointing directly out from it. So we know that the normal is going to be we need it to be unit length, so it's going to be x squared plus y squared plus z squared times x, y, z. Okay, that's the normal. This is not getting easier though, right? So this is a difficult function to compute. So it's worth to switch to spherical coordinates. So we're going to define our set D is going to be in theta phi space, and and there we're going to define phi to be, is going to go from 0 all the way to pi, and theta is going to go from 0 to 2 pi. Okay, that's pretty straightforward. So recall spherical coordinates. I'll draw them out here. If we have some point on the sphere, right there, that angle there is going to be our phi. That angle is going to be our theta. And we need x then is going to be, we can draw our function r, our x, y, and z is going to be of theta phi is going to be sine, and this is just the coordinate transformation, sine cosine theta, sine phi sine theta, and cosine phi for the z coordinate. Okay, so there's our mapping R. So again, what we have here, our set D is going to be from 0 to 2 pi, 0 to pi, and that's the phi axis, and that's our theta axis. And we're going to map with R, and that's going to map to the sphere. Okay, so the question then is, how do we find R? The next thing we need to do now is so this method of finding the norm maybe not so easy, because remember what we really want is we're going to define it in the set D of f dot RU cross RV dA. All right, so here's our R. Let's compute RU. So in this case, U is going to be equal to, we'll call it phi, and V will be equal to theta. That just simplifies our notation. So RU, or R phi I should say, is going to be, and I'll write it out here, cosine phi cosine theta. And for the second, for the y coordinate, it's going to be cosine phi. We're just taking the derivative of sine, and then we'll multiply that by sine theta. And then finally, that'll be negative sine phi. Okay, looks good there. Now we have to do r of theta. Okay, r theta, let's give ourselves enough space here, will be, we have to take the derivative, this will be negative sine phi sine theta. It'll be sine phi cosine theta, because we're taking the derivative of sine, it'll become a cosine. And finally, the derivative with respect to theta of the z coordinate will just be 0. Okay, good. So now we have those two. What we have to do now is take the cross product. So let's do that really quick. So the cross product, so r phi cross r theta, and that will be, and now I've pre-computed it here just to save some time. It is sine squared phi cosine cosine theta sine squared phi sine theta, and it's going to be cosine phi sine phi. Okay. Right. And now we need to write down what f is. So I said f before was equal to z, y, x. And now we have to just translate that into, so z again was going to be cosine phi. We just had to transfer that into spherical coordinates. And y was sine phi times sine theta, comma, and finally the z coordinate is equal to x, which is going to be sine phi cosine theta. Okay? All right. So now we need to take the dot product of these two things and integrate. So our total flux is going to be equal to the integral from 0 to 2 pi times, and the integral, the double integral from 0 to pi of f dotted with the vector resulting from the cross product of r phi cross r theta d d phi d theta. Okay, so let's compute this all the way through. So we have to multiply all these terms out. So again, I'm going to skip a few steps here just to make the notation more compact and make our work more compact. And I've pre-computed some of these things. So it's going to be 2 sine squared phi cosine phi times cosine theta, all right, plus sine cubed phi times sine theta, all in a big parentheses, d phi d theta. All right, so what we're seeing here then is we see a product. There's this part right here that's all in phi, and that's in theta. We see that's in phi, and that's in theta. So what I can do then is break this up a bit. What we have is I can keep this integral on the outside. I'm going to put a cosine there, and that's coming from here. And that's going to go outside of the phi integral. We're going to get this 0 to pi of cosine phi. Oh, there's a 2 there. That 2 times the sine squared phi. And then we'll call d phi. And then we have a plus, and then we put a sine theta times integral 0 to pi of this sine cubed term, d phi. And then on the outside of the whole thing, a d theta. Okay. Like that. Okay, so we have this integral here in phi and another integral here in phi. So it turns out if you do a u substitution on this one, if I do u is equal to sine phi, you'll get a du d phi is equal to cosine. But now when you evaluate 0 and pi, what are the limits of integration? It becomes 0 and 0. So then we get a u squared du over this, so that whole thing. So this whole thing goes away. It's 0. So we don't have to worry about that integral anymore. Now this part right here, a little bit more complex. This takes a bit of work to do. I'll pre-compute it, and I'll just say that this thing is equal to 4/3. Okay, so you can compute that straight away. It takes a little work and a few trigonometric identities, but you can get it. So what's left then is computing this whole thing. So that becomes 4/3 times the integral 0 to 2 pi of sine theta d. Sorry, I made a mistake here. That should have been sine squared right there, right? So that's a sine squared. That's a sine squared d theta. All right. So from here, you can compute this pretty much straight away. That's 4/3, 0 to 2 pi. And I'm going to use a trigonometric identity, and I'm going to call, that'll become 1/2, 1 minus cosine 2 theta, d theta, which then becomes 2/3 times theta minus 1/2 sine 2 theta, all evaluated at 0 to 2 pi. This part goes away, and we're just left with 2 times 2 pi over 3, or rather 4 pi over 3. So that's the result. And again, that's the total flux of this vector field here through the circle. So we're going to see this is an incredibly important tool in vector calculus, and will really help us when we're thinking about flux of fluids. It's going to help us with what we call conservation principles. When we want to know how much stuff is going through a region, we can put a sphere around it, if that's a region of interest, and then calculate how much is going in and going out, and the net flux going through things. It'll be very important for electric fields. And so on. So this is a really important tool that we have, and this is the integral. So this integral right here becomes incredibly important for us. So thank you very much.